Hello. Hi everyone. Wait. Hi. Can you hear me? Okay, great. Uh, okay. I think the agenda for today is basically to look into whatever we were actually doing last in the last session. So we actually looked into few of the problems for back propagation and how do you update the neural networks and those kind of things. uh, we will take it forward from there. We will solve one problem based on back propagation with some basics, and then I think we'll move to the newer topics which were discussed, like filters and corner detections and all those things. In between, what we'll do is we will see that why filters are actually required, and we will visualize the filters for ResNet and see uh, like uh, how the ResNet actually learns the features. Then at the end, I think I'll touch upon Ransack. I don't think that is covered, but it's there in the, I think, one of the questions. So if you guys know about Ransack, I think we can skip. But if you want to have understanding, I think we can cover it in the session. So today's session might not be that long, but uh, yeah, I think it would be good starting point for for the classical methods for computer vision. And I think we have been discussing this for a while, but if you guys have any questions or anything, just post it on the discussion channel, so that whenever we take the next session, we have the questions priorly, and then we are able to discuss them in this session. So it will be more useful for not only you but for the other peoples as well. So and it also create a sense, um, give me a sense that where you guys are struggling. So um, it actually helps to structure things better. So yeah, feel free to raise any question, queries regarding any topic, or do you have any specific question, then I think yeah, you can ask, but do not directly ask the assignment question, so that might not be helpful. uh, okay, let's get started. So what we are looking here is basically, uh, you have a neural network which is given to you, and there are few questions will be asking and seeing that how the this chain rule will get executed. So let us say that you have it's a two-layer neural network, and what is happening is these are the W1 and W2 are the learnable weights. So basically neurons in MLP, and the filters are filters in CNN, right? And you have given input X, uh, and so for ith instance, ith data point, the input is called denoted as the xi. So whenever you're training actually using multiple uh, data samples. So what you do is whenever you compute the loss, you not only compute for one data sample, but you take the average of the loss over the batch size, or eventually while seeing the whole data set. So the total loss is basically sum of all the losses of individual samples. So that's why this instance came into picture. So you compute these things for every data sample, right? So what you do is you multiply X with your neurons and W1 and add the bias term into it, so you get a intermediate representation, that is Z1. You add non-linearity to it. So in this case, the inner layer we are using ReLU, and so and you are doing active, applying non-linearity of z1, you get a1, which is the output of activation unit. Then you pass this a1 to the next layer. In the next layer, what you do is like you multiply with w2 and add bias. You get the intermediate representation after layer 2. And then what you do is like you apply a sigmoid function, sigmoid activation on z2, and you get your output. So right, and this predicted output, you check how good your prediction is. So what you do is like in this case, this is called as the binary cross entropy, right? So what you do is like you compare it with respect to the like the ground truth y, which is this yi for that ith sample, and your predicted is basically y hat, right? And what you do is like you compute loss. This loss is basically binary cross entropy, and you do that for all the samples, right? So so suppose there are m sample in your data set. So what you do is like for all the m samples, you do uh, sum up the loss and compute the average loss for all those samples, right? So the problem definition is clear, right? Like what is the premise we're working on? So it's some sort of a two-layer architecture where it is providing y, you have x as an input, then using this y we are computing loss, right? So let us look at the what kind of like intermediate steps we have. First, let us see what is the shape like which is given to us. So well, x is basically, let us assume that x is a shape of dx comma 1, right? So because it says suppose you have image, generally when you feed it to like a neural network, what you do is you flatten it, so it comes into it. So image is 228 comma 28. So what you do is like you flatten it in a form that like it is what is 28 comma 28 comma 1 full transpose, right? So basically what you do is like you just flatten it and pass it to the neural network. So yeah, so your x has dx uh, like points, right? And what it's given to us is the like the number of uh, nodes in hidden unit is dA. So z1 basically belongs to dA comma 1, right? So what we are actually answering first is like what is the shape of w1 b1 w2 b2, right? uh, so let me just say, write it down for you. w1x plus b1, where x is basically dx comma 1. So you have to identify what is the dimension of a number of basically neurons in w1 is d dA, I guess. Yes. So any thoughts what should be the dimension of w1 and b1? Anyone? Sorry, I didn't get it. So B1 is, yeah, yeah. I mean, so every node has a bias term, right? So if there are DA nodes, so every node has a bias associated with it, right? Makes sense, right? So W1 can be DA comma DX, where DA is the number of neurons, where DX is number of data samples, right? Makes sense. DX is number of features, yes. Yeah, yeah. So yeah, yes, I meant that only, number of features. Makes sense, right? So because when you multiply, you'll get Z as DA comma 1. So the B also has a dimension. Is it clear? Any doubt in this? Am I audible? Okay, great. So I think let's uh, move to Z2 basically. So Z2, W2, and it should be somewhere, somewhat. A1 is coming here, and you have a bias term, which is, sir, I guess the numerical value is, these are numerical values. No, I think, who just ask, sir. So Abhinav is saying that I guess these are numerical values, W and not numerical values. So we are actually looking into uh, the dimension of these, right? I hope it is clear, right? So X has DX features. There are these are the neurons. So there can be multiple neurons in a layer. There are DA number of neurons, right? And in this case also there will be some sort of a DA mapping. So these are basically matrices, and these matrices will have numerical values. But overall, like we have to first identify, right? Whenever we are creating a computational graph, right, you have to define what should be the metrics, and like how do you initialize these matrices. So you need to have an understanding of the dimension first, right? I hope it is clear, Abhinav. Okay, great. So next is basically what we are looking is, so we are looking at the dimension of A. So the non-linearity does not change any dimension, right? So it just changes the value. So it scales the value basically. So the dimension of A will be dA x. dA comma 1. So what should be the dimension of W2 and B2? Here in W2, what we are doing here is we are basically mapping it hidden to like Y, right? So it is this layer. So you have DA neurons which are coming, and we are basically kind of outputting a single uh, like neuron, which is basically predicting the Y hat, right? So because the Y hat is a single output which is a scalar, so we have to be mapping it to. So the second layer is basically this only, right? So second layer is basically mapping the hidden unit which are coming to the output. What if we say that like it is DA1 comma DA, and B2 is 1 comma 1, and does it make sense? Is it correct? Is it correct, or do you have any changes? Like we do any changes here? Right. So what we do is, so given a dx features, what we have done is we have mapped this dx features to dA features, and then mapped it back to one scalar which is y hat. Right. So there is one input layer, there's one, this is, these are basically your W1 weights, these are your W2 weights. And corresponding to this layer, you'll have biases, right? For each neuron, you'll have bias. I mean, if it is not clear, I think it's a good time you speak up, so that like I think the next part of the problem makes sense to you. Anyone, any doubt? Okay, let's move to the next part, right? So next part, what we are seeing is like how do you compute the derivative of loss with respect to y hat, so which is our predicted, and what we'll do is like we will basically compute it for like a single sample, then generalize it for the the all the m samples, right? So and we will denote it as the delta 1, and we will use this all these deltas when we were computing the chain rule to see the overall derivative of output with respect to the input. Okay, so let us write what is basically j here. J is some sort of y log y hat plus 1 minus y log of 1 minus y hat. Yes. Sorry. J is basically, this is L, and J is basically 1 over M summation 1 to M. Right. So what we are asked is what y hat, right? So what we'll do is like we'll substitute this value here. Okay. So this can move out. Y hat log of y hat plus 1 minus y can also move out. Y hat log of 1 minus y hat, right? So log of x is basically derivative of log of x is basically 1 upon x, right? So y by y hat plus 1 minus y, 1 minus y hat. This we will denote as delta I, delta 1, I guess. Yeah, so this is delta 1 and I, because we are computing for all the i's. So this is basically the derivative of BCE, right? And if you remember, for mean squared error, it's 1 by 2 y minus y hat, right? Some sort of this. Does it make sense? Anyone? Any doubt? Okay, let's move ahead. So this is the first part, right? So what we have done is like we have computed the loss with respect to our predicted, like the predicted sample. So y hat. Now let's, what we'll do is like we will just move step by step in a backward way, and like, and the end we will eventually see like how does the chain rule turns up. So next is like, how do you compute the derivative of y hat with respect to z2? Let us see what is y hat and what is z2. So y hat is equal to, y hat is basically equal to activation, oh, sorry, and this is sigmoid, right? So I think in the last session, what we have seen like what is the derivative of sigmoid. So what we need to compute here is dz2, and the activation, sorry, the derivative of sigmoid is sigmoid of z2 into 1 minus sigmoid of d. So the derivative here is sigmoid of z2 1 minus sigmoid of z2, and we will call it delta 2 when you are doing it for all the i's. Make sense, right? Okay. So next we are actually looking at 2 with respect to a1. What is z2? Z2 is w2 a1 plus b2. Okay. w2 a1 plus b2. So what we are required to compute is a1 w2 a1 plus b2, and if we compute the derivative it will turn out to be w2, right? Let's call it delta 3. Okay, great. So now we'll go one step back. So what we are required to compute is derivative of a1 with respect to z1. Let us see what is a1 is. So a1 is basically the ReLU operation. ReLU of z1. So any thoughts, or like what should be the derivative of ReLU? No, not one. So the ReLU operation is like something like this, right? So what happens in ReLU is, so for z greater than equal to 0, we say it's 1. For z less than 0, it's 0. Makes sense, right? So here the original value is x. So this we called as the delta 4i. Next we are moving one step backward. We want to compute delta z1 with respect to delta w1. Z1 is basically w1 x1 plus b1. So z1 is basically w1 xi plus b, right? So we'll call it delta 5. Makes sense, right? Okay, so now what we are required to do here is we are required to compute loss with respect to w1, right? Then only we will be able to update w1, right? So what we are required to do here is, like, we are required to compute a chain rule. So let us see, right, uh, what are the factors which were there. So there was z1, which is w1 x1 plus b1. So there was a1, which is basically ReLU of z1. Then there is z2, 2, which is basically W2 A1 plus B2. There is A2, which is sigmoid of Z2, right? And then you have a Y, you have a loss term here. Yes, Y should be, okay, it's not A2, it's Y. You have a loss term 1 minus Y log 1 minus Y. Then you have a J, which is basically averaging over all the samples different time, right? So what we are being asked is like to compute J with respect to W1, right? So we have to see that like how does the W, so the J changes with respect to the W1. So we'll go step by step whatever we have seen, right? Like what we require is like first is like how do you compute uh, J with respect to Y hat. This was the first thing we did, right? Yep. Next is what we will say that like how does the Y hat changes with respect to Z2. This is the second thing we did. Yep. Now we will see that how does Z2 changes with respect to A1. Now see that how A1 changes with respect to Z1. At last we'll say that like how the Z changes with respect to W1. Makes sense, right? So that's how you actually like do the chain rule. So we have kind of decomposed this operation into series of multiple small operations. So what we are doing here is in like directly seeing the effect of changing W1 on J. What you're doing is like we are first seeing the effect of changing J with respect to what is being predicted. What is being predicted is Y hat and it's dependent on Z2, right? Z2 is dependent on A1, A1 is dependent on Z1, Z1 is basically dependent on W1. So that's how you basically back propagate. So you have computed all the like you have computed the gradients of J with respect to W1. So what we'll do is like simply uh, substitute all the values here. So you have delta 1, this is correspond to I guess delta 2, delta 3, delta 4 and delta 5. And how do you update your weights? So weight is basically some sort of in this manner, and this is your learning rate. Yeah, so I hope the overall process is clear. If you have any doubt, I think this is a good time. I'll just summarize it once and then we'll move to the next thing. So, I mean, any doubt, just let me know. Is that clear, or do you want me to go over it again? Yeah. Okay. So I'll just summarize whatever we have seen in this, and let us see. Like, I think it's a good exercise. More you are exposed to these kind of problems. That in the last line you wrote W minus. So Abhinav has a question. Let's just see what he's asking. W minus eta, right? What I have written is like W minus. Uh, so basically, yeah. So it's a update rule, right? Whenever you are uh, like, suppose this is your loss surface, and what we are trying to do here is we are trying to get to the minima here, right? So we are doing some sort of a gradient descent. So with the objective is like, for what W, how do I change my W such that like my loss is minimum. So what you do is like, after each iteration, whenever you are like computing your gradient, you update your weights, and you come to a point where your weights are at a local minima of this loss surface, so that like your loss is basically minimum, like ideally close to zero, but practically very small. So this is the update equation basically. Yep. Okay, right. So basically, the takeaway here is, um, in like any form of neural network, whatever we are seeing is like, how does the loss changes with respect to our learned parameters. So basically W1 and W2. And what we generally do here is like, we compute this gradient, that is uh, derivative uh, of j with respect to W, which is your initial weights, and also and do the this weight update using this equation. And how do you do it? Like, you do it with a like chain rule. So you go one step back at each step, right? So what you do is like, you compute derivative of j with respect to your predicted samples with respect to your intermediate representation z2, z2 with respect to a1 with respect to z1, and z1 with respect to your w1, right? And then you update your weights. Okay, makes sense, right? Okay, so next I think we'll move to uh, like looking at the features basically. So we'll move to filter based methods. uh, okay. So yeah. So basically what you need to look here is, you can see my screen, I hope. So I have opened Google Notebook, and you should be able to see it. Just Yeah, I think it should be clear. So what I'm showing here is basically, so when you actually look at the so resonate, I hope you are aware of resonate. So deep neural networks or deep CNN based architectures are basically built on feature or filters learning, right? So the initial, so ResNet has, sorry, CNN has 3 cross 3 such filters, right? And what you do is like you do some sort of uh, like feature learning. So ResNet actually learn some sort of edges in the initial layer, and as we move deeper into the architecture you kind of build on top of these features. So the first uh, few layers are basically some sort of a or corners computations. So once you have identified such edges, you can actually start making sense out of them. So like the next layer actually take these edges and then make some inference out of them. So suppose like you are actually doing a face recognition. So what my initial layers will actually look into. So my initial layers will be actually looking at the certain edges, some maybe some hair texture, some gradients of hairs, like how does the hair align. Those kind of features the initial layers learn. Then we move to the second layer, which actually start making sense out of these initial features, where uh, some sort of a textural understanding takes place. And then we go deeper into the architecture, then you there are few layers, few like filters which be actually looking at the eye, and then maybe the nose, maybe ears. So those kind of features they start to figure out. So it starts with very granular level and then it goes into the much more abstracted levels, because the receptive field basically become larger and larger, so as we go deeper into the architecture. So uh, like uh, these neural networks actually learn these things on their own. But earlier what used to happen is they used to define design these filters. So there were some edge detection filters were there, some sort of corner detections, some texture detection filters were designed. So it was itself a field of research, but now everything has been learned on their own. So I just wanted to show you like what kind of features this ResNet is learning, right? So like if you can see this, right, like there are two blobs here, one is blue, another one is orange, and it's some sort of learning some sort of a diagonal edge, right? And similarly, this can be basically you have a black, you have a high gradient, and then a low gradient again, some spike. Basically, it's kind of trying to capture and this orientation. Similarly, this filter is basically trying to capture the spike and this the other uh, rotation. So like you can see that like it's they're kind of trying to figure out the colors, they're trying to figure out the edges. Maybe when you go into the next layer they'll trying to figure out the textures as well. So here it's basically simply the vertical edge detection, this filter, right? I hope you can see my cursor. And let me see if I can increase the resolution. Yeah, zoom in. I hope it's clear, much clearer now, right? Like if you can see, this is simply the vertical edge detection. So these are few of the filters which I have visualized. So there are more filters. You can see that like they should be learning some sort of a basic feature identification on their own, and then the later layers build on top of them. So but earlier what used to happen is like everything was basically designed by hand, and then they use them in different kind of problems. So yeah, so that was the state of the art back then, but now everything has been learned on its own. So these are the features for ResNet. So I mean, you can also visualize what your like when you train any CNN based architecture, just like visualize what these layers are learning, and you'll be surprised to see that like what kind of initial features these layers are learning. Just check for different kind of data sets and different type of modality. So suppose if you're working on like medical images, maybe histopathology images, just see what kind of features these initial layers are learning, and then just see for natural images what kind of features are they learning. So I mean, because the modality changes the in I don't see there will be very high change in the initial feature, because most of them will be trying to capture some sort of edge information or some gradients. But if there are any features which are based on the color, so in histopathology images which are majorly pink, you will see that the filters will be focusing on the gradients of pink. And if these are MRI or X-ray images, you will see that the filters will be more focusing on the gradients of like gray, right? Because the modality actually requires that. So these are basically the learned features where which ResNet actually learns, and we'll go back to see the importance and uh, see that like if we can actually design some filters. Let me just share the my iPad screen. Okay, right. I hope you can see my screen. Let me just stop sharing this one. Perfect. Okay then. Like suppose we are designing a filter which actually kind of reduces the intensity. So what are your thoughts? Like what should be the values here? So some sort of a darkening filter which actually reduce the intensity of the image. Maybe image is too bright, and like you don't want like all the pixels to be activated. So maybe some sort of dampening you want to do in the image. Any thoughts like what kind of filters like one should design? Can you just write the values? What is the gamma filter and how does it work? So Shagun suggested gamma filter actually. So let's see. If you want, you can actually unmute and just explain. Okay. I'm not sure about gamma filter. I think I see this as a Sobel filter. Uh, okay, so you are saying that so you are saying that let's just see that one. So Shagun suggested this filter 1 1 1 0 0 0 -1 -1 -1. Mm, why do you think that this will work? It will still be some sort of a gradient, right? These kind of features it will detect. So it will detect the edge. Would subtract some value from the input pixel brightness. Uh, it how does it subtract some values? Okay, let us say that like it's what is the input image, maybe let's say all 5 become 0. Yeah, okay. What if I have 5 5 5 0, maybe 5 5 5 here as well, or maybe opposite actually, 10 10 10, and then 5 5 5. So actually it will reduce the, yeah, makes sense actually, makes sense to me. So what is it is doing is like we are kind of averaging, but also some sort of a subtraction is happening. So when you convolve this, let me just write it very cleanly. Let us say it was 10 10 10 0 0 0 5 5 5. Then if we convolve this, so the resultant will be actually 10 plus 10 plus 10 minus 15, right? 5 into 3. Okay, so this actually goes uh, 30 minus 15, right? 15. So this actually goes here. So your updated image some sort of, this region become 15, right? So this doesn't solve our purpose, right? This also will become 15. Still still, like suppose we are needed to do zero padding, let us say at this point we're uh, computing at this point we are computing. So if you are doing some sort of a filtering here, you put your uh, CNN base filter here, then everything outside is 0, right? So 1 1 1 here, 0 0 0 here, minus 1 minus 1 minus here. So actually even with 0 padding this becomes 0. So I think this will not might not work, right? So what if, yeah, so what if you do some sort of a scaling operation? What if we say that, like, let's just scale by zero point 0.5, so every value becomes 1 by 2 1 by 2 1 by 2. Or maybe if you want to scale further, you can actually change the value 1 by 9 1 by 8 or something like that. So some sort of a scaling operation might help. Let us see if that helps. So you just put it here, 5 by 2 plus 5 by 2 plus 5 by 2 plus 15, 5 plus 5 plus 5. 15 plus 7.5 by 9, right? It do some sort of a damping. So I think what should be it is 22.5 by 9, some sort of a 2 point something, right? So this uh, this we have moved actually, but if we actually look into the other points, they should dampen it. Let us just try 555 something like that. So this I think should turn out to be something smaller than whatever we are kind of observing now. So because we are reducing the intensity by half of all of them. Makes sense. I think I might have confused you. So, yeah, but like if you do some sort of a scaling which is less than one, it will actually creates some sort of intensity reduction uh, effect. Any doubts in this? Confusing. Yeah, sorry actually for confusing. So let me just rewrite it. So what we are saying is like we want to create some sort of a darkening filter. So what is a darkening filter? It basically reduce the intensity of the image. And how do you reduce the intensity? Suppose you have an image which is completely white. So 255 is the maximum, right? Like the so the RGB range is between 0 to 255. So we are at this point. So it's very high brightness. Same, same here, right? And if you convolve this image with this filter, what should you get? So what you'll do is we'll just place it here, right? So 255 by 2, 255 by 2. This will get for 9 times. You'll get 9 and you normalize by 9, right? So this should be somewhere between 128. So if you do it for all the values, I mean, yeah, like at least the internal values where you have all the you have complete overlap will be dampened by 2 128 only, 255 by 2. So what we are trying here is we're kind of trying to reduce the intensity of the image, and if you want to reduce the intensity, just scale the intensity. Does it make sense actually? Chandra. Okay. Yeah, great. I mean, yeah. So just feel free to interrupt me anytime. Like if you have any issue, yeah, it's good. What about the smoothing filter? So, so any idea about smoothing operation? Maybe Gaussian. Uh, all ones also. There will be required padding. So padding is at the image side. So padding is at the image side. But when you're designing filters, you need to define the characteristics of the filter. So basically, what you're doing here is like whenever you have an image which is uh, some dimension, you you can only start with this point, right? But what about these things? So you do a image padding whenever you're computing for this, where because you're placing the filter at this point. But if you generally what you do is like you have a zero padding, these will be anyway zero. So what you're drawing is like just concentrating of this region, sorry, this region. So padding is required actually for last filter. Yes, yes, yeah. I was talking. Yeah, yeah. So for image, yeah, definitely for all the corners, padding is required. Okay. So we were at smoothing filter. So any guesses? So maybe some sort of a mean filtering, all ones. Makes sense, right? So what it does is it's creates some sort of a averaging effect. What it does, it's kind of damps your like your like high edges, so it makes like your image kind of smooth. Makes sense. Any doubt? Okay. What about the left shift operation? So what you want is like when you multiply this filter with the image should shift left. So this should become blank. Mm, no. So Shagun is suggesting 0, 0, 0, 0, 1, 1, 1, 0, 0, 0. No, because you are kind of doing this operation. I still be looking at the peaks. What we want is like shifting operation. Any other thought? You want to shift your image to left, right? So your first row is like empty. Mm, mm, Second suggestion is 0, 0, 0, 0, 1, 0, 0, 0, 0. It will do actually nothing. It will keep your image same, because suppose you are placing this 3 cross 3 kernel on the image, on the pixel you are like placing it will be 1, rest will be 0. So it it is essentially doing nothing, right? It is keeping the image intact. Yes, Abhinav, yeah, it's correct. Yeah. So let's do it mentally, right? So you have an image, and I'm computing for this point. Let's say this point. So what is happening here is like everything is zero, zero, zero. This is one. This is zero. 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 Right. So what I'm essentially doing is I am replacing x, this, so suppose this has the value x, with this value, right? So your updated image, so suppose this has a value y, right? I'm multiplying y with 1 and updating the x. So x basically become y here. So what we are trying to do, we are kind of essentially moving everything to the left. Make sense? That would, okay, sorry, yeah, 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 sorry, I missed left and right, yeah. So this is when you're kind of moving it to the right, yeah, 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 and the opposite will be, yeah, sorry. 0 0, yeah. So this will essentially move it to left. Okay. Yeah, it makes sense right now, everyone? Mm, okay, I assume it makes sense, and I think next we move ahead. Let me just see. Okay. So this is some other question, right? Like, so what we are doing here is we are kind of applying a Gaussian filtering, and then we are computing the gradient after applying the Gaussian filtering. The Gaussian filter, what it does, it basically does like smoothen out the things, right? So in general, we apply shift. Where in general we apply shift filter? Uh, I have, so some sort of image manipulation. Uh, yeah, some sort of like image manipulation. So this shift filters, uh, shift shift rotation, these filters are basically applied whenever there's an image like manipulation is required. So I think in robots, the camera actually, whenever you're kind of moving, the camera change, so you need to map everything into the original space. So that's where you either want to shift or you either want to rotate. So these operations are essentially required there. So I'll just say that, like, yeah. Next question. So we apply a Gaussian filter to the image on the zebra nose and compute the derivative. To obtain each of the image, we varied the standard deviation. of the Gaussian filter. Given a fixed size kernel, let's say it's 3, standard deviation of the Gaussian filter decrease from left to right. So if we are moving from leftmost to the rightmost, what should be the effect of standard deviation? Any comments? I mean, just read. Meanwhile, I'll just open up the next notebook. Okay. So Shagun is saying that we are kind of reducing the width. Uh, mm, Let me just share a notebook with you so that we can actually do it and see. So what I am doing here is, I hope you can see my screen, right? I have taken the same image and I am kind of increasing the standard deviation. What effect are you seeing, right? Can you make a guess? What effect are you seeing? Can you see that there's a reduction in the sharpness? The edges are more wider. So this is much sharper, right? They're much wider edges now. Yes. So what will happen is like, yeah. So if you can see that, like, it's very sharp for when the if we do Gaussian filtering for a smaller standard deviation, the edges are sharp. But when you're doing it for wider, basically the variance, then you're kind of smoothing out even more. So that's why your edges become slightly spread out. But like if whenever the standard deviation very small, so the edges are like very sharp. Was you correct? Let me just see. You said something in the starting. You say that like the yes, yeah, yeah, you're correct. If you basically reduce the standard deviation, the images are much more sharper. Okay, I think yeah. So this is with respect to filters. Let me just like have you guys studied ransack? I mean, because I can see there is one question in assignment based on ransack. So have you guys studied it? Not yet. Okay. Okay. Let's what I'll do. Let me just not till week 7. Okay. So let us just okay. Let's just start with ransack, right? So uh, yeah. So what happens in ransack is basically uh, uh, suppose you have a set of points, right? And what you want to is like you want to fit a line into those set of points. So basically it's some sort of a fitting problem, but what you do is like you iteratively like it's some sort of a sampling problem. So what you do is like you sample 2 points, right? Try to fit a line along them and say that like is it the best fit or not, right? Instead of trying to find some like so uh, like you can fit a line in a set of random points using maybe some logistic regression problem where you are kind of identifying the you kind of learning the like slope and the slope and the intercept, right? So this is that is basically a learning problem. But like suppose you want to earlier what people used to do here is like they what you do is like you have a set of sample like points. What you do is like you uh, randomly select 2 points which you called as the seed group. Let's say uh, like you select s point, in this case the s is 2, so you have selected 2 points. And let me just see let me just show you how does actually the data look like. Suppose this is the data you have, okay, and what you want is like you want to fit a line into this data, okay. So what people generally do is what they start with selecting 2 points, then based on these 2 points they select it, they draw a line, and you find out what are the inliers to the model. Inliers is that like the points which are within a threshold reach from this line, and you assign some sort of a weightage to it. So suppose there are 10 inliers and but there are 20 outliers. So outliers are the points which are far from the line, and you repeat this process with multiple times and eventually find out a line which has the maximum number of inliers, right? So let us see what is happening here, right? So the algorithm has basically 3 steps. So first one is sample. So what you do is like you sample 2 points. Let's say I'm just sampling these 2 points. And the second one is like the so what you do is like you draw a line basically in between these 2 points, right? And then you have a scoring function. So you based on these 2 points which are basically my inliers and which are my outliers. So inlier, suppose these 2 points are within my threshold, so I am fine. Like these, I'll consider these two as my inliers. This also as my inlier, but these 2 points which are far away from this line are called the outliers, right? And I'll keep on repeating this process again and again till I'll find out a line which has maximum number of inliers. So what? Let's see step by step. So what we have done is like we selected these 2 points, we have drawn a line which is passing through these 2 points, And we'll see that like based on a threshold delta on the both side of the line, we'll call these blue points which are inside inside this threshold are called as the inliers. So there are total of six such points. So 1, 2, 3, 4, 5, 6. So this is one such case. Now I'll select some other point, right? So these 2 points suppose I have selected, and the delta are there is present on the both sides. So in this case I have 14 inliers. I am only missing these 2 points. So this is basically the true distribution where the samples are sampled from. These points are sampled, and these can be the cases where these are noises which can be added to the data. So you kind of identified which is the true uh, distribution which from which these points are samples, and you're kind of fitting the line. So this actually helps when you're doing some sort of edge line detection. So you have multiple edges and you want to create a line out of those edges. So you have many points corresponding to edge, and what the goal here will be like to find out a complete line which satisfied that connects these multiple edges into one line. So the line detection problem was solved using this ransack uh, algorithm. uh, yeah, I think I took over did a very quick pass, but like I hope it's straightforward. You sample points, you fit a line on these 2 points, and you identify based on the threshold which are inliers, which are outlier, and you identify those points which has maximum number of inliers. Make sense? Maximum inliers in the, say suppose you have a threshold of delta on both the sides, right? So the what are the inliers are these blue points are your inliers, and these red points are your outliers, because this is some sort of a margin which we are kind of tolerating. So the delta is the margin which will tolerate on both sides. How many lines can be there? So you just fit one line at the end. So you have one line which is basically fitting your data, but you try out with various lines. Suppose there can be a line between these 2 points, maybe these 2 points, and then you compute a cost that like how many points are there inside the inliers, inside this delta threshold, and you pick those points which are basically has the maximum inliers. That's it. Is it clear? Okay. Okay. Others, is it clear? Yeah, so this is basically the ransack algorithm. I mean, people use it for line fitting in multiple domains. So, in some sort of a point cloud, also you have certain points, and you want to make a sense out of these points. You try to fit a line, maybe a curve, and find which is the best fit. So, um, people use it it's robust as well. It's good actually. Let me just show you example of one sec. So I mean, this is the algorithm I have written, right? So this is, suppose this is the initial data, right? And we're trying to fit a line onto it. So there can be multiple iterations here. So this is after 5 iterations, we're kind of figure out what is the, like, the line which is fitting the data, but we're still finding out the optimal case here. So if you look here at this point, you have 1 2 3 4 5 6 7 8 9 outliers, right? Then we say, like, let's like try to move the line in some other way, right? So this is the second line which after 20 iteration has been fitted. Still there are many outliers. Still, like in the third, after 50 iterations also there are some outliers, and eventually it kind of identified what is the best fitted line. In this case you have only 1 2 3 4 5 6 outliers are there. So uh, like you have actually identified a line which has basically fitting the data and has the minimum number of outliers and maximum uh, inliers. The red one are the basically outliers, and green one here are the inliers. So I mean, the steps are also very simple, right? So you sample 2 points, you like based on these 2 points you fit a line on them, and you find out, identify, you have a threshold, you define a threshold. And let's see where I have defined the threshold. So I have defined the threshold as 10 here. And what you do is, like, if the point distance of that point from the line is less than threshold, then it's an inlier. If the distance is greater than that threshold, if the distance is being calculated using old geometry, what is the old geometry? Yes, yes, yeah. Distance, yeah. So basically, you have a point, you have a line, you basically project the point onto the line and find out the some sort of a perpendicular distance to the line. Makes sense, right? Any doubt in this? I think last point, I think I just wanted to share this uh, like image. I mean, it's very helpful for me to visualize it. Suppose, I mean, in case of, if you might have studied the Harris corner detector, right? So there are two lambdas. So there is lambda 1, lambda 2, right? So I mean, to visualize, uh, I generally use this image. So in case where either lambda 1 or lambda 2 is greater than the other one, uh, like very very high. So lambda 1 is very high as compared to lambda 2, lambda 2 is very high compared to lambda 1. So basically you're kind of moving only in one direction. So either you're moving horizontally or you're moving in the, like, vertical direction, or even like if the plane is tilted, you are kind of moving only in the one direction, so prominently in the one direction. So in those cases you will get a edge only. But in the cases where both are like very high. So in that cases you are like kind of moving in both the direction, and you have gradient present in the x and y as well. So in that case you are basically in the at the a corner. So I mean, just so there is a very good tutorial of Harris corner detector on OpenCV. So just check out if you have any doubt, so that like you actually get a practical intuition about it. And there is a notebook here as well if you want. In I'll just let me just show that to you. So I mean, so open CV2 has this corner Harris function, which you can directly use to compute the corners. And if you can see, these are the corners it has detected. I hope these red dots are clear to you. You're able to see the red dots. So I mean, there are functions which actually do the task very easy. But do try out this tutorial, which is actually very good. So let me, if you can actually show you. Just try this. So this image has been taken from here. Um, this actually will give you a good practical understanding uh, how things work. So I mean, I do recommend using it. Okay, I mean, yeah, that's what I have for this week. I mean, this is the good time we discuss. If you have any doubt, if you have any recommendation for next session, I think this is the good time you can actually pitch in. So, anyone would like to contribute or any suggestions? Uh, yeah, maybe I think next week we will be looking at Swift features, Swift surf, those kind of traditional methods, and then we'll try to classify images based on those features. Like what we'll do is like we'll extract out features from image, then build a classifier to okay, so build a classifier using CNN. So Shagun is asking if we can actually do a backpropagation through CNN. So let me see if we can actually find a good example for CNN. So people actually generally don't discuss CNN because I mean, once you see it, like it's very like easy. So maybe next session, I think I'll just show you. I'll just show you at that point of time rather than telling. Uh, so that actually will like improve the like understanding. So yeah, it's basically the transpose of your filter. So the gradients are basically transpose of your like filter, or in some case image. So both of them runs alternatively. So let me see if we can actually uh, some sort of a router also, because you're some doing some sort of max pooling operations. So how do you extract key features from ultrasound images by maintaining spatial and temporal information? uh, so Chandra is asking, how do we extract keyframes from ultrasound videos by maintaining spatial and temporal information? So uh, so what okay, so I'll just tell you what we used to do. So I have not worked in ultrasound images. So basically, a heuristic would be that you look for the images which you look for the frame. So suppose you have a video Let's just answer one by one. So let's just answer Chandra's point. So what he's asking is like you want to extract out relevant frames, uh, like from a video. So I mean, I don't want to go into particular modality, but uh, you like whenever you're extracting information, you want to extract different information. So like distinct information. So suppose there is a person, like you are doing some sort of a like video analysis or video surveillance, and if there is no movement at night, you don't want to extract anything out of those frames. So at the night there is no one moving, it's completely like silent, so that silent frames will not give you anything. You just want to extract out information where there is some movement is happening. So what people generally do is they do some sort of a background separation between the frames. So if you have frame number 1 and if there is a frame number 2, if there is some sort of a, you define a threshold, if the changes between frame number 1 and frame number 2 is like greater than the threshold, you assume that there is something which has happened in the frame number 2 which was not there. So maybe someone has walked into frame number 2. So you want to extract that information, so you define some threshold, and then like if you succeed, like if your the change is greater than that threshold, you retrieve that. You So this generally people do for summarization task, where you have long videos and you want to summarize what might be the important information. So that is something which people generally do. Let me see how you can do in any other way. uh, you can actually do some sort of a feature based similarity as well. So suppose you have frame number 1, you extract out features. You have frame number 2, you extract out features. If the features are very small, there is no like the frames are essentially very similar, so I don't think then you need to like keep the frame number 2. But if there is some deviation in the features, then I think you might want to keep that frame. So the crux is you can extract features in any way. You can extract some changes, so the you want to capture the changes in the frames, right? So you just keep or extract frames where there is some additional information which is being added into like as compared to the original frame you which you keep at the. It is maintaining spatial and temporal. I tried this but not working accurately. Okay, so uh, I I don't know. Like maybe we can talk offline about it. You can discuss more about the problem. Uh, in general tasks, that's all I can say. Uh, I mean, it doesn't make any sense to train a model to do some sort of a summarization. Maybe because the data also you'll not have sufficient data. So yeah, try using some foundation model, extract, pass on the your image, extract out features, and do some sort of a similarity matching. If the two frames are very similar, then just identify, you might have to identify the threshold. So instead of image level, do it at the feature level. Just see if that works. SSIM actually will work for image level. So I'm suggesting is like what you do is you have a frame number 1, you pass it to some sort of a like architecture, maybe some for foundation model. For what kind of modality are you using? You are using ultrasound videos, right? Just pass it through a network or architecture which has seen ultrasound images, extract out features of that frame. Then when you move to the next frame, extract out features for that as well, and then you compute some sort of a cosine similarity between them. So SSIM actually works in the image space only. What I'm suggesting is to move the problem into the feature space. Okay, okay. So next, Shagun asks, would basically need domain heuristics to define important frame. I think, yeah, he has some domain heuristics, but yeah. So what I answered is in a more general setting. So that might, so there's some kind of problems, right? Like in the video, so there is some you want to summarize a video, so what are the frames you basically look into? So, or maybe in the CCTV, right? So it runs 24/7. So if you want to summarize it, you cannot watch like all the uh, for 24-hour video. So you might want to actually capture the frames where the activity is happening. So I mean, that's maybe what he's looking into. So Abhinav is asking, sir, back propagation is little bit difficult for me to understand. I think, I mean, I would suggest just go and see the previous sessions, video. So in that we have discussed, I think, two three problems where we have actually computed the gradients and see how does the back propagation take place. So I mean, I would encourage you to go and see that video. So it's I mean, the link is there in the NPTEL portal you have, and the video is there in the YouTube. So you should be able to access it. And maybe next session we will try to see if we can actually do CNN based back propagation that actually will like clear out things. So I think I understand. So back prop is like difficult. Uh, in like I'll have to see if we can in the next few sessions also we can actually solve at least one problem based on that, and then hopefully the confidence will build up for you. Anything else you guys want to add? So I think assignments as a programming assignment is also up. So uh, yes, some problems which would help in a second assignment. I think, yeah, I'll look into it in maybe next week. We will try. Yeah, we will try next week. Yeah. So ransack was something which was not covered, and there was one question. I'll see if I can find out more problems which are closely related to those things, and then we can cover. Sir, how can we get some sample questions for NPTEL exams? I mean, I don't know actually. I don't know. I don't think these are in public space. Just see the lectures. Uh, yeah. Uh, I mean, there are resources, right? Like if you search for books on these computer vision, you will see good books. If you want, I can post few of them, uh, like in the discussion, forum. You can refer them, but I don't know. I don't have access to those questions. But like if you, yeah, I don't know. Anything else, or shall we close? Any last comment, suggestion, something? Okay, then I think we'll close it here. Thanks everyone for joining, and see you next week. If you have any questions, any doubt, just put it in the discussion forum. Okay, thanks. Bye bye.